Welcome. I'm incredibly excited to see you all here today. My name is Duchin, and I'm a math professor here at Tufts and a member of the Metric Geometry and Gerrymandering group that's bringing you this workshop. So I have a few welcome remarks before we get started with the actual talks. And thank you so much for coming. It's great to see this theater actually filling up after all this time planning this. I'm really excited that you're here. Okay, so let me start with thanks. So up top you see our major partners. We've worked closely with the incredible civil rights organization, the Lawyers Committee for Civil Rights Under Law. Many representatives of the Lawyers Committee will be here this week, but I want to single out my old friend, the inimitable Kristen Clark, who's the executive director of the Lawyers Committee. And doing incredible work to safeguard voting rights around the country. And the Jonathan M. Tisch College of Civic Life here at Tufts has been a partner, a major sponsor, and just an incredible support in putting all this together. Other sponsors to whom we are extremely grateful include the Sloan Foundation, the Educational Foundation of America, the Scholars Strategy Network, the College of Arts and Sciences at Tufts, and the Program in Science, Technology, and Society, One Virginia 2021, and many, many individual donors. Thank you so much for your support. So who are we, the organizing team? MGGG is made up of these four people: Mira Bernstein, myself, Ari Nee, and Justin Solomon. Half of us with Tufts affiliations and half with MIT. All four people have worked incredibly hard on this. So thanks very much to us. At the Lawyers Committee, I mentioned already Kristen Clark, but I also want to thank Megan Gall, who's the staff social scientist at the Lawyers Committee and has done a formidable amount of work for this workshop. At Tisch, Dina Alexander and Jennifer McAndrew have been a huge source of support. We have a crack team of summer interns: Asaf Barnatan, Tali Falk-Judson, Nathan Foster, and Emily Sim. Thanks to them. And then a large number of people who've come in for the specialized session trainings at the end of the week. A little bit of information about the talks. Here we are in the Somerville Theater. And I want to thank Ian Judge and the Somerville Theater for helping us stage this event here. We'll have the talks available by video within a day. So they'll be up on YouTube, they'll be downloadable. In particular, that means, and this is a heads up to all the speakers, talks are very public. The last talk in the theater ends at 12:45, and we want to try to actually get out of here by 1, except those of you who want to stay for Dunkirk. That's what's showing in this theater after that. Notice emergency exits. They're marked in addition to the main exits that you came in through. In the afternoon, there are parallel sessions, and that's going to involve some hard choices. We've had a number of questions about which parallel session people should go to, in particular what the prerequisites might be, and the best thing I can say is go to one and try it out. In the course of my talk, I'll plug a little bit of the math that will get delved into more in today's parallel session, but you should give it a try and see how they go. The evening lectures and the afternoon parallel sessions are on campus, and your program or the website will give you a map that shows you where. We've got something set up for questions. We thought it would be difficult because of the size of the crowd to walk around and get your questions orally, so instead there are question sheets that you can fill out for written questions, or you can use your phone, and I encourage you to do this, pointed at tinyurl.com/askjerry. And ask us whatever questions you might have. Ari will be collecting those questions and posing them on your behalf, selected questions at the end of the talk. So the talks are 50 minutes and then a 10-minute period for questions at the end. Oh, that's so great that someone's phone just rang because, look, phones off, please. Right, so first, this workshop is on the record. There are media present, which is great, but be aware of that. Please do turn off and silence your phones, or silence your phones. And you should have gotten an email about this if you pre-registered, but there are GIS-related sessions every day Today and tomorrow are intro from scratch, repeats of the same thing, but before you go, you should download QGIS. That's what they'll be using at those sessions. And we are tweeting. So we have a conference hashtag, gerrymandar. Gerrymandar, that's our brand. Okay, I believe that's about it. Except we do have a conference survey that you'll receive by email at the end, and we hope you'll take a moment to fill it out. We're running several more of these workshops, 4 more around the country. We're going to Madison, we're going to Durham, Austin, and San Francisco, and we're trying to learn from each one and run it a little better the next time, so I hope you'll take a moment to fill out that survey. Okay, so with that, I'll change hats and switch over to giving the first talk of this conference, which I'm calling Situating Redistricting as a Problem in Law, Math, and Politics. So that's a lot of ground to cover. Let me get started. So first, I'll just introduce it by describing the slide, the image that you see in the background here, probably well known to many of you. So this is a political cartoon that ran in a newspaper in 1812. It shows a district thought to be gerrymandered. Well, now we'd call it that. It's a voting district drawn by then Governor Elbridge Gerry, who's one of the founding fathers, as it were. And what you see here, if you can read the print, you'll recognize that it's not far from where we're standing. These are places in the North Shore of Boston. And this district was strung together to create a block for Gerry's allies, the Democratic Republican Party. Yes, that was one party. The cartoon was designed to lampoon this as though it looked like a dragon or a salamander, and that's what gave us the word gerrymander. Gerry's salamander became the gerrymander. Okay, so today, by today's gerrymandering standards, this seems positively quaint, right? So the threat of gerrymandering or precision drawing voting districts in particular to meet some agenda. I'll talk much more about what I mean by gerrymandering as we go. But today that threat is really intensified. It's intensified by technology, it's intensified by data and better handling of big data sets. So we have GIS, or geographic information systems. We have maps that are manipulable down to the house level. We have very rich voter data files. We can now know an enormous amount of information about voters, age, race, income, political preference, and so on. And if you overlay the data on the map, you can rig maps to get all kinds of outcomes, and that's what we're here to talk about, right? So there's all kinds of gerrymandering. You can rig districts towards any number of agendas. There's partisan gerrymandering, which is, I think, on everyone's minds these days. But there's also the time-honored racial gerrymandering, or fencing out of minority representation. And then the, extremely prevalent but much less talked about incumbent gerrymandering, or when politicians on both sides of the aisle come together to make safe seats for themselves. So gerrymandering comes in all flavors. Okay, I'm going to focus on the congressional level of districting. This conference is about redistricting broadly, but this is a good place to start. Okay, so there are several elements that you have to establish before you can get towards congressional representation. First, the people have to be counted. And in the US, we do this by census. In fact, that's about the only direction that you'll find in the US Constitution for redistricting. It says that people, representation in the House is to be apportioned according to the respective numbers of the people as enumerated by the decennial census. So this is a map of the US. I apologize, I think it's a little fuzzy, but the slides will also be available later. And what it shows is census tracts, so census units, colored by the population in each. That's showing you where the population, how the population is distributed in the US. I'll say a little bit at this point about that. So every single one of these steps is fraught and has some interesting mathematical issues in it. So how do you count the people, right? The census makes an effort to go door to door and actually check where people are, in addition to sending out forms for people to fill out. But of course, there's still some imputation to do. There's going to be some missing data, and you probably are going to want to correct the census count, and there's been some debate over the years about the best way to do that. So that's already not straightforward, counting the people and saying where they are. The next thing that has to happen is that congressional representatives have to be apportioned to the states. So here's a picture off Wikipedia of the current post-2010 census, the current congressional apportionment. So I don't know how well you can see it, but there are numbers on each state, and the numbers, that's how many US Congress representatives that state gets. So there is a rule that says no state should get 0, so even the least populous states have 1. And California over there has 53, right? Because there's a whole lot of people in California. The color coding is just about the change between the 2000 and the 2010 census, but it's not relevant to the point that I'm making now. Okay, so if you were to take all those numbers and add them up, they'll add up to 435, the number of representatives in the House. Okay, and then but I should say, I already said every step is fraught. Apportionment is a mess, right? So it's roughly proportional to that state's share of population, right? So you have 435 representatives, and you look at what fraction of the US population lives in your state, and you should get roughly that fraction of the body. The problem is probability 0, that's going to give you a whole number, right? So you have to round, and that sounds so innocuous. But when you're rounding small numbers with high stakes, it's a mess. And so there have been over the years, in fact, the very first presidential veto in US history was about the first apportionment scheme, how to round those numbers up and down. Okay, so there's a whole long and interesting story to do with how we arrive at whole numbers of representatives for each state. Okay, but finally, once we have those numbers, we have to actually divide up the states. So this last picture is an overlay on the first, showing those 435 districts outlined in yellow, right? So there's nothing to do in Montana, so you just see the state outline, because they only get 1 rep, but California's got to have 53 of these districts. So this is a rich story, but this week we're focused on that last step. Once you have the state's apportionment, how are you dividing it up into districts? Okay, so I'm a mathematician, so I want to set up redistricting as a math problem. Let me do that in a really simple way first on this slide, and then we'll get into chewier and more complicated math as we go. So at its simplest, this is about partitioning a population. Partitioning just means you take the whole population and you split it up into subsets. But here you got to keep track of the attributes of that population. So I'll start with a set that I call the population, a set of nodes or points. And those are going to have attributes, and those attributes can take on some number of values. That's a lot of language, so just to give an example, I might take the attribute of color, taking on the values red and blue, and the attribute of number, taking on the values 0 and 1, just for a simple example. So here's a population of 40 nodes, and their attributes are pictured, right? So hopefully that makes sense. Okay, so now the problem, and of course the way that I've drawn it suggests how I'm going to chunk it, but the problem is to partition the set into blocks, and I'll call those blocks districts. Okay, and then we can ask, for each district, it's going to have a representative. And what I've done here, so look at the leftmost district or block, and you'll see there are more zeros than ones, so the representative is a 0, and there are more reds than blues, so the representative is red. You see what I've done? I've just taken the predominant attribute values in each district and used that to designate the representative, because that's how we do voting. We have districts and then a single member representing each district chosen by plurality vote. Okay, so this is, of course, the toyest of toy models. In reality, there are literally tens of thousands of census blocks per district, not 10, like in this picture. And they're organized spatially over the globe, or maybe a small enough portion of the globe to look kind of flat, right? But they're spatially organized as well, and they cluster in funny ways. They're not uniformly distributed. And now you need to district that much, much more complicated, giant discrete set of data. Okay, so some questions you can ask are, how well does the district level attribute distribution reflect the population, right? That's a key question you might want to ask. So in this case, 0 has 45% of the population, but only 25% of the districts, right? Red has a bare majority of the population at 52.5%, but 75% of the districts. And so a question you can ask is how reflective, first of all, is it a goal to make the attributes of the district level as proportional as possible to the population? And if that's a goal, how best to achieve that is a question. Does this make clear? Is this clear as a math setup? Okay. All right, so like I said, you can have goals for this, and then we'll add some constraints. So proportionality, as I just mentioned, make the districts representative. So that's a pretty natural goal that you might have. But on the other hand, you might want to gerrymander. And here by gerrymandering, I'll just mean set up your partition to make as much or as little as possible of some attribute at the district level. So if you visualize that example from the last slide, suppose I really wanted lots of red zeros to be representatives. Well, then instead of taking those interval chunks of the population, maybe if I'd chosen districts that weave in and out of the line in some special way, I can make as many red zeros. Maybe instead of 1 red zero, I can get 2, or if I'm really careful, maybe I can even get 3. Right? So that would call gerrymandering. I want to extremize, in this case, maximize the incidence of some attribute at the district level. Okay, so those are kinds of goals you can have. And to make those harder, we're going to constrain the problem. So for instance, the district should have equal population. So that's taken to be a constitutional principle actually clarified last year by the Supreme Court in Evenwell v. Abbott. So it's taken very seriously that districts should have really, really close to equal population within a state. Districts should be described, we think, by contiguous regions with no holes, or what mathematicians would call connected, simply connected regions. That's a sort of traditional constraint on the problem. And they should be not too eccentrically shaped, but what does that mean? Okay, so that's really at issue here if you want to study this geometrically. Okay, so the math sits in context, right? And you're really engaged in a kind of mathematical malpractice if you're approaching this problem without paying attention to its political and legal context. So I want to highlight in particular the kind of political philosophy that's activated here. So every constraint should activate some kind of political value, some idea we have about how representative democracy should work, right? So for instance, equal population, that speaks to something you might call representational equality, that all the people who are to be represented by congressional reps have about the same fraction of a representative that they account for, right? So representational equality of all the people whose interests are supposed to be taken into account. Now, how about this geographical division? So let's pause and think about that. Not, you know, if you've looked around the world, you will have noticed that not every country does it this way. Has geographically delimited chunks that elect a single member. That's, in fact, it's not a very common system. But why do we do it this way? That does tap a value that we have about how representative democracy should work. I argue that you can defend that with the idea that bare majorities shouldn't dominate. So for mathematicians, I'm trying to get into, trying to allude to classical probability here in the form of central limit theorem or the law of large numbers. Here's what I mean. Imagine you have a population and just 53% want to vote one way, let's say, and the other 47% want to vote the other way. Suppose you were to split that population into 10 districts, okay? So it feels like that 53% majority should get 5 or maybe 6 out of 10 representatives, right? Suppose we didn't do geographical division, but instead, suppose in this state, the state of, you know, mathematicum, suppose in this state we assign people a district randomly. So we give people a random number 1 through 10, and that's the district that they're in, right? So they're sort of distributed over the population. If we did it that way, the 53% majority would be converted into a total lock on the representation. And that's because classical probability tells us that when you're dealing with a large population, the level of each attribute in a district is going to be very, very near the total population proportions. So we have 53% statewide. We tend to have 53% in each of the districts, and that's enough to win in every single district. okay? So if we totally abandoned geographical districting for random districting, we'd have total dominance of even the barest majorities. And I think we should say that it's a political value, that we don't want that. In shape, well, I'm developing an argument that eccentric shape detects gerrymandering and other extremization agendas. So anything you're trying to do shows up in shape as part of what I'm arguing. Okay, but these are far from our only intuitive or philosophical principles or normative commitments, by which I mean thinking about what should be rather than just what is, right? We might want proportionality. We've been talking about that on previous slides. We might want some kind of partisan fairness. We might want like a level playing field for the two major political parties that exist in this country. Maybe it's hard to say precisely what that means, but it's at least a philosophical ideal. There shouldn't be a structural advantage to one party or the other built into the system. We might prefer competitive districts. We might think that makes for a healthier democracy. And if all of these are kind of fairness principles, we also might want some governance principles built in. So for instance, in governability, we might not want a nearly deadlocked House of Representatives because that maybe doesn't tend to govern very well or very effectively. So to that end, we might even imagine that the system should build in some kind of seat bonus so that the party that gets more votes gets a little bit of a cushion in its majority in the body so that they can actually get laws passed. These are all things we might want. I'm not saying we as a group are consensus committed to any of these, but they're possible principles. And then there are legal parameters, and none of these four are actually in the law. There's no law yet against entrenched systematic partisan advantage. There's no, the Supreme Court has even clarified explicitly, there's no requirement for proportionality in a districting plan, right? So none of these things are built in, and I say yet here because, as many of you know, partisan fairness is on its way to the Supreme Court. I think October 3rd, they'll start to hear this case, Whitford v. Gill, which looks at the partisan structure of Wisconsin's legislative map. So a lot of people are looking to Whitford as a really important case to maybe have a legal standard in place to sort of constrain partisan gerrymandering as such for the first time. Okay, so there we were in philosophy land. Now let's get down to brass tacks. Let's gerrymander, how to gerrymander. So now I've decided I want to extremize the share of representation for some attribute. What do I do? So the two most famous happily rhyming techniques are called packing and cracking. Here's an image to show you what that might look like. So in both of the two images here on left and right, I have a 6x7 grid, and half the squares have stars. Okay? And it's the same configuration of stars on the left and on the right. And what I've drawn in here is two different districting plans. In the plan on the left, the red plan, can you see the shading here? Okay, so in the plan on the left, stars had half of the votes, and they've converted that into half of the seats in this plan on the left. That sounds about right. But in the plan on the right, which I'm proposing as a kind of gerrymandered plan, stars have had the pen of control for the line drawing, and the lines have been drawn in a way that actually gave them 1, 2, 3, 4, 5 out of the 6 seats, even though they only had half the votes, right? Incidentally, this image comes from a paper that Mira Bernstein and myself recently wrote about that Wisconsin case that's on its way to the Supreme Court. So this paper will appear in Notices of the American Mathematical Society, but you can already get it online in case you're interested in hearing more mathematical analysis of the formula that's at the heart of the partisan case. Okay, but what's going on in these pictures for the purposes of this talk is you can get excess representation for team star, but you do it at the expense of more eccentric district shapes. So you see nice plump districts here on the left, but on the right, they had to become a little more stretched out, skinnier, tentacled, a little more eccentric. Okay, so what do packing and cracking actually mean? Let me just try to illustrate that in these pictures. How did Star do it? What is the secret to Star's success over here on the right? Well, what you'll see is that they packed their opponents into one district. So they gave up one district to the blanks. You guys see that? And in that district, it's almost all blank population, right? So blank has been packed or stuffed in to that district, producing a lot of vote wastage for blank team. And then the counterpart strategy to packing, so that's called packing, when you stuff your opponents into a district so that they waste lots of votes there. And the counterpart strategy that goes together with it very well is cracking. So in all the rest of the districts, the blank squares, the blank voters have been dispersed in numbers slightly too small to predominate, right? So that's another kind of vote wastage when you have lots of votes but just not enough to win. Okay, so by making those two things play off each other, packing your opponents into districts and then cracking or dispersing the ones that are left over, that's a way to maximize your representation. Okay, so the intuition that this slide is trying to set up is that any agenda, and by the way, that's agendas noble and nefarious alike, right? So nefarious gerrymandering or noble proportionality, any agenda that you really push to its extreme is going to cause eccentric shapes. Okay, so now let's talk about how we evaluate those shapes. So the term of art in redistricting for the analysis of shapes of districts is compactness. So it's a traditional principle. You'll hear more about that from Megan Gall and others this week. Many state constitutions and lots of statute around the country says that districts should be reasonably compact. That is almost never defined. It's just trying to get at your intuition of something that's like munged together nicely, as opposed to being, you know, tortured and tentacled and spread out. Okay, so if you want to approach this like a mathematician, you might actually want a metric by which you're going to measure this elusive thing called compactness. So there are many kinds. There are over 30 in the political science literature. And actually, that's been one of the problems, is that there are so many, and they compete, right? But one kind of metric, as you'd expect if you're sitting here with a math PhD, one kind of metric is isoperimetry. So it's a classic theorem that for any shape at all, you can ask me later what shape means. If you take this score here, this formula, 400 pi times the area over the perimeter squared, if you just take that formula, you will always get a number that ranges from 0 to 100. And so we can treat that as a score of compactness. The idea is plumper things have more area, so they're up at the high end of the range. Those are our good districts. And the really wacky, spread out, tortured ones are going to be down living towards 0. So here's a diagram to illustrate that. So I built this. First of all, you can see a circle all the way up at the top. So circles do the best job of enclosing area relative to their perimeter. They're the only things that live right up at the top. And then you see a bunch of other kinds of polygons falling away a little bit in terms of their compactness score. There's a square up at about 75%. And then rectangles that get longer and skinnier are penalized more and more. They're showing up with lower compactness scores. And I've helpfully put some actual congressional districts on the slider to show you where they are. We've got Indiana 7. That's looking pretty square, not bad. We got Michigan's 4th district clocking in at about 37, 38%. Massachusetts 5, we're not quite in it, but we're 2 blocks away. Actually, true fact, the line between Massachusetts 5 and 7 runs through the math department at Tufts. And then there's the scary red zone of things that are 5% compact and below contains a number of US congressional districts, including the notorious North Carolina 12th district pictured there. It looks like a river, but it's not. Clocking in at about 2.9% compact. That's worse than a M built out of squares. Okay, so this is a thing you can do, and it produces a compactness score, and at first glance, maybe that seems reasonable, but it's not great. It's not great for a whole lot of reasons, and one of them is that perimeter is kind of not a thing, I want to argue. So here, a congressional district, you have to think about how it's actually given to you as data, right? And then once you have your hands on that data, is it a polygon and it has a simple perimeter that you can know, right? It's actually, the data's a bit of a mess. And you'll hear more about this later in the week, but you know the famous coastline effect, that how long the coastline of England is depends on the size of your ruler? So we actually took a look at that and looked at the shapefiles for congressional districts and how much the perimeter changes when you zoom in. Spoiler, a lot. Okay? So perimeter is actually pretty unstable, and Justin Solomon and others will be talking more about those ideas as we go. Okay, so maybe you could try something else. You could look at convexity, or how indented a shape is. So here we see a bunch of population, and in blue, what's called the convex hull. It's the boundary of the convex hull. That's the figure that would contain all possible line segments between points in the district. So how different a district is from its convex hull is kind of a measure of indentedness. And there are lots of possible refinements that you could make on that. But then you could worry that maybe that's not really capturing what you want, because after all, there are many legitimate reasons for non-convexity, right? And to be discussed down the line if you want to hear more about that, but that's a possible quibble against the convexity approach. And then a third thing you could try is dispersion, or how spread out the district is. If the district came to you discretely like this, you could just sort of look at the average distance between all the points as a measure of how much it sprawls, right? Or if you take the district to be a smooth sheet, like in this picture, you can do the same analysis with an integral. You can just take a kind of moment of inertia and figure out how spread out it is. How far apart do the points tend to be from each other? And mathematicians will recognize that image as a hyperbolic one. And what's going on here is you're seeing lots of dispersion. Things are really spread out. And the idea is dispersion should be bad. We shouldn't want sprawling districts. It's kind of an antonym for compactness. Okay, well, the thing is, though, all of this, everything on this slide, first of all, it's super classical. You know, sometimes mathematicians use the term classical to mean before I got my PhD. But in this case, it's the real kind of classical. This is all 19th century math. And many have worried that it doesn't really speak to the practical problem of redistricting. So I'm going to rebrand this slide classical compactness. This has something to do with why, if you go around the country, as I've been doing, trying to talk to litigators and legal scholars and political scientists, and you say the word compactness, you should see the looks you get on people's faces. Because there's a lot of worry that compactness is mathematicians off enjoying themselves and not in contact with the real problem. Okay, so in particular, how does compactness play in court? Well, the court has repeatedly accepted compactness as a principle, but complained about every possible definition that it's been presented. So the court has derided, tortured, irregular, bizarre, irrational shapes, and has thrown out maps over and over again on the basis of shape, including quite recently, but has not established a shape standard. Here are 4 images from Bush v. Vera, which is a case in that notorious Shaw line of cases that you'll be hearing more about from Ellen Katz and others this week. And in this case, the 2 districts on the left, which were majority-minority districts, were thrown out as unconstitutional on the basis of their shape, while these 2 majority-white districts on the right were kept. Okay, so what's going on? What made these unacceptable and those okay? Well, it was never quite clear. It was a bit of an eyeball test. Actually, a little story. So yesterday, I stopped by the meeting of the NCSL, the National Conference of State Legislatures, where they were talking about some of these same problems in redistricting. And I went to a session where the folks from Utah were talking about how maps are built in Utah, and they mentioned compactness as a requirement. So I asked at the end, well, what's your definition? And they were like, we eyeball it. And that's actually typically how it works. It's called a requirement, but then that requirement doesn't have a corresponding definition. So in fact, there's even language in all these cases that I really love where the justices just throw up their hands and essentially say, you know, the math can't help us here. You're asking us to engage in endless beauty contests for districts. Okay, so this is frustration with the math not seeming to be in conversation with the kind of practical problems. Okay, so the math is at risk here of losing contact with what we care about. So I'm going to shift gears for a moment and talk more about the things that are coming up as obviously relevant when people are doing redistricting. Okay, so let's talk about race. So one of the things to say about race is that there's what some people have called, what Bruce Kane and others have called conjoined polarization. So race and party are far from independent variables. People of color tend to vote Dem, especially black voters. Here's a race and gender breakdown of Clinton versus Trump voting. A lot of things to notice there, but in particular, we've got black women voting 93% for Clinton. Right, and here are some images to illustrate how that looks at the level of map drawing. So this is a chunk of Wisconsin, and the units that you see in this picture are Wisconsin's political units of wards. And this is the Milwaukee vicinity, and in this top image we have black voters. The green shading shows the number of black voters per ward, so the darker green is more black voters in a ward. And here's Democratic presidential 2016 voting, and here's Republican. Okay, so this wasn't cherry-picked to show you this effect at its most pronounced. This is an intellectually honest example where we just saw sort of how it turned out. And so what you can see is that, of course, the places with more black population, that's heavily predictive of more Democratic voting. So if you're a line drawer, you can use race as a proxy for party and sometimes vice versa. Right, so they're conjoined in complicated ways. Okay, relatedly, heavily relatedly, cities vote Democratic. So here's a table that I pulled from an analysis by CityLab, and it shows not cities proper, but metropolitan areas. It shows the size of the metro area compared to the Clinton and Trump vote share. And so what you see is that metros with 1 million or more people voted strongly for Clinton. Mid-sized metro areas broke about evenly, and the small metro areas went pretty strongly for Trump. But those large metro areas make up an increasing share of US population. So that's currently 56% of the population, 54.7% of the vote is in those big metros. Okay, the point of this is to say that if you actually want to make maps, you have to think not just about squares versus triangles, but about how to split cities, right? Because cities have really dense population, and how to carve that up is really going to have an outsized impact on the political effect of the map. I thought this was a really interesting piece of nuance. So this shows correlation coefficients by metro area. So you see the ones that are populous, the most populous ones, that's positively correlated with Clinton voting. That's what you're seeing here. But density is an even stronger effect. So not just how populous your metro area is, but how close people live to each other. It does a really good job of tracking with, in this case, the Democratic versus Republican share of the presidential vote. And then I thought this piece of nuance was interesting too. How you get to work is really predictive. Okay, so for people who drive alone to work, that correlates pretty strongly with Trump voting. Public transit with Clinton voting. And that means you really want to understand something about urban infrastructure too, right? So I hope I'm getting at some of the interdisciplinarity of doing this problem in reality, right? Okay, next I want to show you the top 40 US cities. I've organized them by their estimated 2016 population and whether they voted Clinton or Trump. So quick, before I do, how many do you think voted for Trump? Yeah, good, 3. So 3 of the top 40 US cities, Oklahoma City, Mesa, Arizona, and Colorado Springs, and all the rest. And this, what I think is fascinating about this is partly that cities, even cities in red states are blue, right? That's something that you'll see if you look at the data. Okay, so I hope I'm driving home that all across the country, how to split cities is really a fundamental question for line drawers. How does this actually look in the real world? You guys recognize this district? It's famous, the earmuffs. So this is the semi-notorious Illinois 4th District. What does it actually look like in Chicago? Right, you see what we're doing here? We've got Pilsen and Humboldt Park strung together by a highway. Right, so you remember that requirements that districts be contiguous? Apparently highways count to connect them up. Okay, so what's going on here? Well, here's the representative. It's Luis Gutierrez. He's been representing this district since 1992. And up here you can see his vote shares. They are really high, right? So, hey, it looks like the mathematics of studying the compactness of the district has successfully detected packing. But has it? So there's actually a complicated story to this district. I put up this slide to say a few different things. I want to show you how districts look overlaid on the cities. I want to show you how they look overlaid on the representation. But I also want to drive home the point that shape analysis is only going to tell you that someone was trying to do something here. And it's not going to tell you what. Right? So shape analysis is some kind of agenda detection, but it can't tell you the agenda. And actually, this district was drawn by people who wanted to create minority representation for Latinos. So the story just keeps, as you keep delving, you find more and more layers. Okay, so can we put the math back into contact with the reality, with these kinds of elements? Well, I wouldn't be here if I didn't want to say yes. Right? So I want to devote the rest of the time that I have to talking about how to maybe reboot the math and get it back in conversation with some of the realities we wanted to touch on. Okay, so this slide's a little hard to track. After the talk and the question period, there's a video that goes along with this that I'll show, which may or may not make things a little clearer. So let me try to explain what I'm doing here. Here's a question that we can throw out, trying to put the math back in touch with the political reality. Maybe density itself is to blame for gerrymandering. I would even call this conventional wisdom. Legal goddess Pam Carlin uses the phrase, Democrats like to huddle for warmth, right? i.e., they're really sort of densely arranged into cities, and that's going to make even neutral line drawers tend to pack them into districts. That's that intuition. And you might know an influential paper by Chen and Rodden from just a few years ago tried to test that effect with simulation. So that's something that we decided we wanted to think about. So what you see, so we're looking at, one of the many things that we're looking at in MGGG as a research group is the splittability of shapes by thinking about what I'm calling here their packing and cracking loci. So let me just try to explain what I mean. In this image, you see a teal square. And let's imagine that teal square is a city that's densely packed with, we'll say, Democrats. So there's a uniform distribution of Democrats in this city, and it's surrounded by a sea of Republicans, we are to imagine, at a lower population density, okay? The red dot shows a possible place to split this up into districts. So this is just a model. This is just a very simple model. We're going to do more complicated things later. But imagine that where the red dot is, wherever the red dot is located, I split vertically and I split horizontally through that position. And then I build squares of whatever sizes are necessary to get equal population districts, right? So I've got my denser city population, and then I add to it however much of the less dense country population is necessary to create the roughly 700,000 people that should be in a congressional district. See what I'm doing? Okay. So the color scheme is telling you whether it's packed or not. If I locate the red dot all the way over in the corner, then the lower left district is going to be packed with Democrats. You guys see what I mean? But if I locate it too close to the middle, I might have the risk of cracking the population, of creating, maybe, suppose that there were 1.5 million people in this city. If I split it right in the middle, I'd get 375,000 in each of the 4 districts, right? So depending on the population of the city, splitting it in the middle risks cracking or having just a little too few to win. So I should have set my numbers a little lower, but hopefully that's clear, right? So cracking is where you have just a little too few to win in several districts. So, well, you can actually study this, and it's not too hard. So in the square, suppose I vary the red point around the upper left-hand corner. What you're seeing is those 2 curves represent the line, the border line for where you'll be packing and where you'll be cracking in this particular example. So in that region, the population is packed. In that region, it's cracked. Up here, it's packed and cracked. But the good news is that there's a happy zone, right? And so that's the splittability question, like how many places are reasonable to split a city if you're actually paying attention to the packing and cracking that you get out. So, I mean, this is work in progress, but we started to do this with actual cities. So you can take the data of a city and look at what happens when you divide it up in different ways. And I'll show you some cool videos. The point of this inquiry, though, we're trying to tease apart 2 different effects, density and shape, right? Each of those might be a contributing factor to why it's hard to split things fairly. And so one of the things that a mathematician might want to study is how those interact. Okay, video to be shown later. So, here's an intervention that we can make that I actually really care about, so I want to emphasize this slide a lot. So I want to say maybe the wrong turn in those ways of assessing compactness from that slide back a few minutes ago. Maybe the wrong turn was how we conceptualized what a district is. So in those slides, typically, in the classical definitions of compactness, you think about a district as a shape, just as outline, right, that you might be able to draw on a piece of paper. Think of it as a region in the plane, right? But somehow that's missing everything about the population density and the transportation lines, and that's missing all the stuff that you care about if you're just paying attention to the outline. So I want to propose some ideas for how we can come up with a new abstraction, a new geometric object that actually sees the things we care about. Okay, so to capture that, let me so here's a picture of Southern California. This is Long Beach, and this very populous census tract is a military base down here. But I bring up the picture to say, suppose I wanted to chunk this up into squares. When a lot of people first approach this problem, they're like, why don't we just use squares, right? Suppose you wanted to chunk this up into squares. Something you could notice is there are places in this picture where a square actually seems to fit pretty well with what's going on in the data. But, good luck trying to find a natural place to put a square where the population is denser. So this square might be very reasonable. This square is not. It just cuts right through a dense population. It pays no attention to communities of interest, to keeping political subdivisions together. So maybe not all squares are created equal, and we actually want to see what's inside and not just the outline of a district. Okay, so how could we do that? Well, let's think about our data. So the data comes to us discrete. I mean, people are discrete, not continuous. And you can get your data from a number of sources, but a very reasonable place might be from the census. After all, we have some constitutional guidance to look to the census when we redistrict. And also, the census is national. It's ostensibly nonpartisan. It's ostensibly, and we hope still, well-funded. And it's not trying to take your money, right? There are other sources of data that will sell you, right? There are companies that will sell you their data sets. So maybe the census is a good place to start because of those factors that I just highlighted. Well, if we do that, the census units are blocks. Those blocks are grouped into the creatively named block groups. And those are in turn aggregated into what are called tracts. So these are just 3 different levels of population aggregation that the census gives you, okay? So maybe a really natural thing to do is just to make a graph once you've picked your units. And here I mean graph in the mathematical sense of vertices or nodes connected by edges that show the relationships, not the y equals x squared kind of graph. So maybe we want to form a graph to see the guts of a state and its district plan. So I want to highlight here, this conference is not about us selling you a mathematical product. Actually, one of the things I'm really proud of is that we've brought a lot of excellent mathematical minds here together to brainstorm and think and generate ideas about this problem. So I want to highlight this as something that we as a math community should be thinking about. What are the edges that you want to put on this graph? So a really simple thing you could do if you're taking census blocks is just put down an edge when 2 of them are adjacent, when they share part of their boundary. That's easy, but that doesn't mean it's the right thing to do to capture what you care about in the data. Maybe instead you want edges weighted by the travel time or the distance between 2 blocks, and maybe that's capturing more of the relevant information. Or finally, commonalities. Maybe you want to see edges representing political or demographic commonalities or shared interests between blocks, and that's going to show you what you care about. So all of this is up for grabs, and I think this is an excellent time, and we have a lot of great high-level attention focused on this. Let's really think through what the right abstraction is, because then you can do geometry on it, and it'll tell you things you care about. Okay, so let me show you how this looks when you try to carry it out. This is North Carolina's second most infamous district, the first congressional district, shown at the census tract level. Okay, so what you see here in black is the graph I was talking about on the last slide. There's a node for each census tract, and I've connected two when they're adjacent. Okay? What's outlined in red is the district. So which tracts are in the picture? Well, we tried different inclusion thresholds. This picture shows tracts that are where at least 10% of the population votes in MC1. Does that make sense? We had to have some, because the district slices through tract lines, we had to have some standard for when to include the tract. So this is 10% inclusion threshold. So what you're seeing is maybe some weak, I don't claim this is a smoking gun, but some weak evidence of gerrymandering. This map doesn't respect tracts very much. Maybe that's not too surprising, and it would look better if we went down to block groups or blocks. But I'm just trying to show you a simple image to illustrate the concept. Okay? Notice cities show up here in this picture. And they show up because since the tracts have about the same population, city tracts, those that are in denser, more densely populated areas, the tracts will tend to be smaller and closer together, and so they'll show up as these kind of tight clusters in a graph like this when I lay it out, in an isometric embedding like this. And so I've labeled what city it is that's showing up. So when you see really dense-looking clusters in the picture, you're seeing part of a city. Here's that NC12 again. It's stringing together Charlotte, Winston-Salem, and Greensboro. And there's a few things that are fun to notice about the way this picture is reassembled by its tracts. So the district itself, remember the district is outlined in red. The district itself is whole free, but the tracts, if you take all the tracts together, you've created some topology, which is kind of interesting. Okay, and then for comparison, here's a relatively innocuous looking district from North Carolina's map. This is North Carolina's 8th, which also touches Charlotte. But so you can see here that the district and its reassembly from tracts look more similar than they did in the others. Does that make sense? Okay. So what's the point? The point is that when you have the right kind of object, you can revisit your ideas about what compactness ought to mean, and it's going to be kind of doing a better job of tracking relevant information. Quick example. Remember way back when we were comparing area to perimeter, right? And I complained that perimeter isn't very meaningful. Well, once you have a graph like this, you can redefine it. You can say, well, consider all the tracts in your graph. And say that one of them's on the boundary if some of its neighbors are in and some of its neighbors are out. And then as a notion of perimeter, you can just count the number of tracts on the boundary divided by the total number of tracts. That's some kind of comparison of perimeter to area done discretely, right? And it's going to be more meaningful than Steiner's 1838 theorem was going to give us a few slides ago. So here, if you look at this on the tract level, you'll see, I don't know, maybe a third of the tracts are on the boundary. And maybe that's now inching towards being a smoking gun here for NC12. Almost every tract is a boundary tract, right? Okay, it's all perimeter. Okay. Okay, so I have just the right amount of time left, which is almost none, to give you a teaser for a new approach to compactness. So I want to propose curvature as a possible new approach to compactness. And the idea is that these graphs, they're not just nodes and edges, they also have some kind of intrinsic shape. And that shape connects up to the ideas that we saw earlier, including isoperimetry and dispersion. So here's a beautiful example that was rendered by MGGG's own Justin Solomon. Here you see different numbers of triangles arranged around a central vertex. This also decorates your program, of course. So you see 3, 4, 5, 6, 7, 8, and 9 triangles arranged around a center vertex. And so all of these are just graphs that sit in the plane. And you could easily find these in one of these tract graphs I showed on the previous slide. Well, what you see above is what would happen roughly if you tried to actually build them with origami out of fairly rigid triangles that are equilateral. So equilateral Euclidean triangles, and you tried to build them, they would take on a shape, right? So if you put 6 triangles around a vertex, well, that lies flat. That lies perfectly flat. But on the other hand, if you put fewer triangles around a vertex, those fold up, and they make part of a tetrahedron or some other appropriate solid. If you put in too many triangles, so there's too much angle around the vertex, then to make room, you need to create this kind of saddle shape that you see, and you see it getting more and more pronounced as you try to pack in more triangles. Okay, so in math, we think of this as a spectrum of curvature, from positive curvature down to negative curvature, and 0 sitting there in the flat world. So 0 curvature is flat things. As a mathematician, I live down here in the negative curvature world. And here we have saddle shapes, but what's characteristic of those shapes is things like high perimeter and high sprawl. In fact, those exact same ideas that the classical compactness scores were trying to get at. And in case you're wondering, can discrete curvature do as good a job as classical smooth curvature at correlating to these things? Yeah, there are theorems that show that it does. So some of my own work, for instance, shows that even in a discrete setting, negative curvature gives you high sprawl. And we're actually trying to carry this out. So here's a map of Massachusetts with neighboring pairs, the edges between neighboring pairs colored by what's a relatively new idea called discrete Ricci curvature. If you want to hear more about this, come to the afternoon math parallel session. We'll talk a little bit more about how to develop these ideas. And so you can just wonder, how do district lines play with these curvature maps of the different states? Okay, so this is just a teaser. This is work in progress, and if you want to hear more about how it's developing, you'll have an opportunity. So thank you. So before pivoting to questions, I'll just remind you, so we're MGGG, the Metric Geometry and Gerrymandering Group, small team that you'll be seeing a lot this week. We do research, publication, interdisciplinary collaboration, which we take really seriously, and outreach and education. We could use your support. We've made this conference free, and if you want to give us a donation, here's the tip jar image that goes along with that. Our website will tell you how to donate. So thanks again for being here, and now let's ask Jerry.
Yes. So if you don't have access to the internet at the moment, then please raise your hand if you have a question, and we'll send a volunteer around with a slip of paper for you to write it down. Our first question is, why does travel time matter if all voting and polling stations are local?
If all voting and polling stations are local? Okay, yeah. So why does travel time matter? So if you think about what people actually have, so it's a districting principle that we want to keep people together who have some shared interests. So one thing to say is, I talked a little bit about how you get to work and how that's reflected in how you vote. But you could also think, if you've been paying attention to the news recently, you've seen that New York City's subway seems to be falling apart before our very eyes, right? And you'd want the people who have an interest in there being resources devoted to the upkeep of that subway, or say Boston's own tea, to be able to vote together. So that's one thing to say about, that's not directly a defense of travel time, but that's one thing to say about the relevance of transit systems, is that people on common transit systems constitute potentially, arguably, a community of interest. But another thing to say is that, distance as the crow flies doesn't necessarily track with how cohesive a community is. In a city, how long it takes to travel from one place to another might really tell you something about the natural shared culture that's represented there. So it's one of many ideas for how to actually get at information about how people are, where people are and what they care about and how they hang together in clusters.
How does the census choose how to group blocks into groups and tracts?
Okay, so that's a black box to me, but I learned yesterday at NCSL that the census takes suggestions. So this is great news. This means that if you, like we are engaged in really trying to understand the data and find the anomalies in the data, the census is actually responsive to, hey, this census block is splitting a natural community in half. You should probably move the boundaries here. Okay, so the census has a giant and changing team of people, of demographers, who really think about how to neutrally and naturally carve the population at its joints, so to speak. But they also take feedback from people in those communities. So one thing I'm hoping is that we'll encourage, inspire, and connect people to actually get their hands on this data, because the 2020 census is right around the corner, right? And we want the best possible data coming out of the census because it's the data that constitutes the object of study.
Is there an intuitive way to communicate curvature in a courtroom setting?
We're working on it. Yeah, so let me just sort of address, though, rhetorically, why. So there's a worry, those funny looks you get from people when you start talking about compactness. Partly those are because, as I said, it is thought, if over 30 things have been thrown at the wall and none of them have stuck, why keep trying compactness? If those 35 things have already been tried, why is definition number 36 going to win the day, right? That's a legitimate source of skepticism. So I'd like to propose that what we're working on isn't building a 36th competing definition, right? Hopefully what we'll be able to do is find a way of thinking about compactness that clarifies and modernizes and unifies a lot of the ideas that have existed in the literature for over 100 years. And I think that we've now spent a good amount of time looking at actual expert witness reports, looking at trial testimony and trying to understand, also looking at court decisions and trying to understand the level of technical sophistication. It can be pretty high. These tend not to be jury trials, but to be bench trials, and the judges tend to be quite respectful of expertise. So if you make a legitimate effort to communicate that what you're doing is bringing together the field and not a 36th competitor, I think you have a fighting chance.
You mentioned an issue with district perimeter being an unclear number. Why isn't district perimeter well defined? Can you give an example?
Sure, okay. So that coastline of England problem, well, some congressional districts actually have coastline, right? And so how long is the coastline of Massachusetts? That's actually a non-rhetorical question if you want to study perimeter here. You need some way to measure natural features because some congressional districts are delimited by natural features. That's one aspect of the problem. And another is, as you'll see again later in the week, just a question of resolution. Even those districts whose shapefiles are pretty clear, piecewise polygons, the polygons change when you zoom in, and you see more wiggliness at higher resolution levels. So we've already seen from real census.gov shapefiles that perimeter can change by a factor of more than 2 when you zoom in. I hope that scares you.
Doesn't your splittability choice, i.e. how much you want to pack versus crack, depend on how competitive you want the district to be? If so, doesn't that run into similar political debates of proportionality versus, say, minority representation?
You are never going to get free of those debates, and that's not the goal. Okay, so this isn't mathematicians trying to liberate us from politics. This is mathematicians trying to be in conversation with politics. So that's one thing to say. And to the rest of that question, yes, all these things are in tension. So the list of different values and even sometimes the list of legally recognized principles, those are in tension and conflict, and you have to weigh the relative importance. You have to put different weight on the different factors. Do we have time for one more?
Sure. For how long and why have districts been determined by legislators and not a nonpartisan committee?
Okay, great. This is the US of A, and we give lots and lots of deference to the states. So the states have a whole lot of control over their districting processes. And it's true that in most of the states, you have the kind of obviously misaligned incentives that the legislature is drawing its own boundary lines. So that's more and more recognized to be a problem. And several states, notably California, have created independent redistricting commissions taking that control away. Another example is Texas, which I think is really interesting. There you have elected judges drawing the boundaries, so that sounds better until you realize that the judges in Texas run for office as Democrats and Republicans. Okay, so 50 states, 50 slightly different ways of doing all this. We hope that there's getting to be kind of a best practices notion that you want to take control out of the legislature and hear input from citizens and from an independent commission, but time will tell how much that catches on. Okay.
I think that's all we have time for.
Great.
We'd just like to remind you that at the request of the fire marshal, there are plenty more seats up in the balcony, but we're kind of packed down here
So to
right now.
speak.
If we could crack and fill some of those for the next talk.
Okay, so the next talk starts at 10:30. Thank you very much.